Not sure if there's anything else on the waiting room video or not. I started a little bit earlier this time. Got to get some newer demos in there. Sounds like we can listen to the Albuquerque traffic though.
Let every nation know, whether it wishes us well or ill, that we shall pay any price, bear any burden, meet any hardship, support any friend, oppose any foe, to assure the survival and the success of liberty.
So, Russia invaded Ukraine last week, and things are all kind of uncertain at this point. Now, I mean, I guess people are killing people every damn day somewhere on the planet, but when one of the groups has thousands of nuclear weapons, it seems like a little bit of a bigger deal. But I am going to act under the assumption that there is a future that we should continue to work towards. So we'll go ahead and do it. I'm going to start by showing a new demo, some old code, but a new demo running on the Lotus 1 and 2. It's actually still running now. We'll just have a little sample of it, and then circle back around to explain why I want to use it as an example for today. First, be robust, then correct as possible and as efficient as necessary. So I want to use Atom Deck. That's what we were looking at, a whole bunch of Atom Decks, little rectangles sort of floating around there, as an example of building bottom up. And where this all came from was last week I took part in this panel discussion, this online panel discussion that Intel Labs was running. And it was fun. I mean, I learned stuff. So I'm going to show like 60-second little clips from it to set up what I want to do with it. And then we'll take it from there. Thank you, Tanya. I wasn't exactly sure how I fit in here. My interest is making computers do new things by themselves because that's cool. By the late 00s, I was depressed about computer security. One bug is all it takes to take over the entire machine. The CPU and random access model is broken. The circuitry of electronic circuitry is incredibly redundant, and therefore software can be incredibly non-redundant. And that's baked into the DNA of computer science. And the claim is, the suggestion is, we have to stop eating the glass sandwich. And here's my conclusion. So rather than saying, you know, it's turtles all the way down, we want to build bottom up and say, you know, it's thermostats all the way up. So build bottom up. And, you know, one of the good things about doing these kind of events is that, you know, I have to refresh the slides and prepare them. And so this time I came up with this 12 steps to robust. And it was the same old thing where I was trying to figure out what my conclusions were going to be so I could put them up front. But then it's just started, you know, seeming like the Christmas song. So I started all fitting it in. And, you know, it's really got all, just about everything. I can pick any one of them and unpack it to get more of the robust first, best effort, and definite scalability story. You know, I'm not going to sing it. You know, I mean, there's actually like little hand gestures that go with each verse and everything. You know, maybe if I ever get to 1,000 subs, then I'll sing it. Anyway, the point is number 3. Build bottom up. You know, saying thermostats all the way up is not a really very clear way of explaining something. On the other hand, saying turtles all the way down isn't really either. So what I wanted to do was take the Atom Deck data structure, creature, agent, code thing, and unpack it in some detail. It's going to go on a while. To see as an example of what building bottom up actually means. And, you know, another reason that I want to do this is there's a phrase that I really have always hated, but it wasn't clear why. And the phrase was solution in search of a problem. And what I kind of realize now is that solution in search of a problem is kind of a sneering way that top-down engineering dismisses bottom-up engineering. you say, so you're working on this stuff, and you say, well, if you make it out of mud and straw and you can make this interesting thing, and then I don't know what you'd use it for. I was originally starting to find a cure for cancer, and now come up with a new way of making a brick. And, it's a solution in search of a problem. And so what I realized finally is embracing bottom-up engineering, building bottom-up. The response to, isn't that a solution in search of a problem? Yes, it is. It absolutely is. And that's good. Why? Because when you take a problem first, when you're working on problem solving, you're handed the problem to start with. What you invariably do, what I invariably do, what we all invariably do, is we cut away everything that isn't really relevant to that problem and just focus on what will actually get us there to whatever specific thing is. And what does that cause happen? That means everything else hangs. Anything that's not specifically in the problem specification is, whatever. Just do something that focuses on the problem. And, the result is, and this is another phrase, this is the complementary phrase to solution in search for problems, is that you're going to end up with, when you do top-down engineering, you're going to end up with unintended consequences. Like that, as if that helps, saying, I inadvertently burned up all the energy in the world, wasting time in order to do proof of work for, proving something to solve a distributed coordination problem or whatever it happens to be. And, it might be unintended, but that doesn't mean that people who are familiar with bottom-up engineering might not have seen it coming miles away. So, yes, let's do bottom-up engineering. Let's own it. And say, the point is, there's all of these things that you can do that are not specific to one particular problem, like taking care of your space, cleaning up after yourself, making sure that you don't pollute your space, making sure that you've got redundancy so that you can get communications, all that kind of stuff, which you can do independent of how whatever specific problem you're going to work on. So that's it. That's the goal. And so here is the atom deck. Each of those blue rectangles is one of the atom decks. That yellow dot there, that is a seed that's actually wandering around looking for enough open space to pop another atom deck. In this particular demo, once an atom deck reaches a certain level of maturity, meaning it's had a certain amount of inserts and removes into its data structure, it pops out 2 of these seeds, and that's it. Then it never does again. It may continue growing, but it won't seed another time. All right, so what is a deck? A deck is a shorthand name for double-ended queue. So it's like a list, or like a line that you go get movie tickets, where you can get on the end of the line and the person at the front of the line gets a ticket and everybody moves up. Except in double-ended, you can also put people at the front of the line and take them off the back of the line. You can go in either direction. And, here I dug this up. This was a program assigned to implement a deck in C++ that was actually due 22 years ago tomorrow. Of course, by the time I left academia, we weren't even implementing decks anymore. It was all you got to do is figure out the name of the class and what the names of the methods are, and off you go. But this was fun. This was good. And it's get the basic deck idea. And, it's got these stringent efficiency requirements that in order to put it, so we got, instead of front and back, we use left and right because it's double-ended. So there really isn't the front, really isn't the back. Insert and remove in order one time, blah, 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 and so forth. Okay. So here was part of the code that I used in the solution that I showed the class afterwards, that we have data, which is a pointer to an array of chars, characters, because that's what we're going to store in our deck, number max saying how much room we've got, and then left and right saying where the head of the left end is and where the head of the right end is. And the key is this little bit of code here. We don't have to go through it all. I mean, first we just say, well, if the thing is full, then, we can't insert. But the key is this part. Data sub left or data sub right, and then manipulating the index, incrementing by 1 or decrementing by 1 in these little tricky ways. But this is where random access memory comes in, going from data and leaping all the way to data plus 1,000,002 if it's a big deck with lots of stuff in it. That's exactly what we cannot do in the movable feast machine, in our asynchronous fallible cellular automata, where we only have tiny little local connectivity. That's all we can see. And we keep saying it's a good thing, but then how are we going to do the equivalent of, leaping out and getting stuff arbitrarily? So how do you make a deck with no array indexes, no pointers? Really, array indexes and pointers, under the hood, they amount to about the same thing. And pointer access brings far data near. Well, it seems like what you have to do. But we have secret weapons. Number one, we're our only best effort. So if we actually get messed up and we can't insert something, we can say, sorry, we can't insert it, and we're allowed to do that. Now, we shouldn't say that unless we're absolutely packed full, but it's up to us. And then number two, everything is alive. Unlike having just the one thing that we're actually doing the algorithm step by step by step, we have a bunch of stuff, all members of the same team. They can work together to bring the data close. So let's take a look at let's look at a cartoon first. Okay, so this is the example of bottom up, building bottom up. So we've got this array, this rectangle, and these are all, unless there's something else in the square, this is AD, AD, AD. That stands for atom deck, atom deck. So this is a rectangle of atom deck atoms, and they're going to work together to do the job. Now, this guy here, PO, that stands for plate operator, and what that does is that actually coordinates the growing of the plate, the moving of the plate up and down, and so forth, that we have seen in a number of different demos that we're all using the same plate operator. So this is how we build up. Once we've got a simple basic thing, a group of atoms that can work together to implement a rectangular shape and take care of important stuff like dying cleanly, staying in communication, healing up when something goes wrong. All of that happens at the level of the plate, and then the plate operator does operations that need to happen sort of just one at a time, like actually moving or growing. And then all of that becomes a base layer of competence, of knowing how to move, that we can add atom deck semantics. That's what ADS is going to do, atom deck sequencer on top. And the ADS just has to know how to get out of the way when the plate operator is doing something destructive, like moving or growing or something like that. And we do that, and I've discussed it in previous T2sday updates, using priorities and so on and so forth. But again, that's all kind of working so that the code for the atom deck sequencer can essentially ignore it. It just starts up and says, can I go ahead, or do I need to wait because something else is happening at a lower level is going through? So here's where we go. Now, suppose here's an atom. This is an atom of something, and the outside world tells the atom deck sequencer it wants to insert it on the left, say. So these two rows up here are the left end of the thing. These two rows down here, nobody's got anything in it, are the right end. So we try to plop this thing right down here, but we can't just put it down. Because why? Well, because we don't know what this is. The flip side of everything being alive is that everything is alive. This could be some kind of dangerous fork bomb or drag that's going to mess things up. We can't just stick it inside an arbitrary atom, stick it inside our data structure and expect everything to be okay. So we don't do it. Instead, we have this two-atom molecule, a dimer that called single quote. And the idea is we take one arbitrary atom, we split its bits basically in half. We put part of them in SQ1 and part of them in SQ2, and then they together they have all the information needed to reconstruct one atom, the atom that's inserted. So what we actually do is we insert and move around SQ pairs rather than actual atoms, and it's only when someone asks to remove one, we take an SQ pair out, we convert it back to an atom and says, okay, now it's your problem. Like that. And so the idea is we put these things. So we say we insert on the left. We might put it down here. Well, now there's a question. If ADS is now asked to insert another one on the left, it's going to run into trouble because ADS and all of these things can only look 4 squares away. So this guy could go 1, 2, 3, 4. He could look out to here, and so it's okay. But you want to keep them in order. The first one wants to come off last if we're doing inserting and removing at one end. So what happens is we want to get this SQ atom moved out of the way to clear space right next to the ADS. So in case there's another insertion on the left, there'll be room for it like that. And so similarly, then they would move out, something like this, get all nice and spaced out so that there's easy room. Now, how did we make these things move? Did the SQs, the single quotes, do they deal with all the details of atom deck sequencing? No, we don't want them to do that. They want to be just general. They have very little behavior of their own. In fact, the only thing that the SQs really do on their own is they know how to die appropriately. If something goes wrong around them and they get the signal that they're supposed to die, well, they take care of themselves and they die. That was actually a bug that the previous version of the Atom deck didn't, the single quote didn't work correctly. So how do these things actually move? They move because of all of these background atoms. These are all alive too. They're not just, dead sitting there. So they're actually like there's one right here, say, in between these two. And it can reach out this farther and so forth. So we get them all going. And now, second thing is, well, suppose we've got, what if the outside world asks Atom Deck Sequencer to remove something from the right-hand end? The right-hand end is down here. Well, there's nothing here. But there is if we had wrapped the cue around this way and said, this is the head of the left end, this is the head of the right hand, and now both of them, 1, 2, 3, 4, are in reach of the Atom Deck Sequencer. So if the outside world says, please remove the right side, then we pull this one and convert it back into an atom. If it says remove the left-hand side, it does this one. If it says insert on the left, we put it in here, and then what happens? Well, they just automatically start making space because that's what all the rest of the Atom deck does and so forth. And it works really well. And, in fact, it's a lot more like the way the movie line works, right? There are no pointers in the movie line. Everybody shuffles forward. Same thing here. And if the line has to wrap around an escalator and head for the ATM, well, that's what happens. So, that all works great. And there's one more little trick, and since I've decided to do a deep dive into Atom Deck today, I'm going to talk about this thing. I mean, because now, again, so suppose we get a bunch more insert on the left, like that. And so these guys all start moving around. And now this one is going to want to roll down like this. And, well, but suppose something else happens. Suppose we now get some removes on the left. So this one's now out, and this one's now out, or, whatever. Let's say this one's now out. And now this guy, he thinks he could roll around to the other side if he wanted to. It doesn't really help. It would be better if he was further down so that he would need to head downhill and get closer to the front by going to the other side. But if he's in this case, 1, 2, 3, 4, 1, 2, 3, he can't see this entire other one. And we can make it even worse. If there was a burst of traffic on the left-hand side, it might be like this. That, this thing is now, how is this guy going to know? Well, let's put it this way. All right, so now we've got two guys here. So this guy would definitely like to roll around and end up here or over here or something like that. But he's not supposed to do it because this is the next guy in line who just hasn't gotten around to walking all the way forward yet. But how is this guy supposed to tell the difference between this state where he's not allowed to move and this state where he should move? Like that. So there's one additional trick. There is a east empty flag that all of the Atom decks have. And you can actually see it in the demo, and we'll look at it in a second. It's a slightly different, slightly darker color when the empty flag is clear, and a lighter color when it's set. So the idea is the empty flag, we clear all the empty flags whenever we do anything, because that means we don't know. The flag is set if we have confidence that everything to our east is empty. And so the Atom decks at the very end, these guys, they know they're at the edge of the plate entirely, so they go ahead and they set their empty flag. And then if this one here is another AD and it looks over, it'll set it. So gradually the east empty flag propagates in. It gets erased whenever it needs. So really what happens is this guy says, is the east empty flag set in these areas? And if it is, then it knows it can go ahead and roll around. And if it isn't, it knows there's something further off to the east that it has to wait for, like that. And so layer upon layer, individual atoms, plates, plate operators, more complex sequencers, manipulating the datum, which are, almost completely passive, except for dying, and so forth. So let's look at an example here. All right, here's one that I grew it from a seed. It's already going. This is the There's the plate operator. It's got a ton of information because it has to figure out, how much clearance is there around me? Is there room for me to move? Is there room for me to grow? That's all the job of the plate operator. All the atom deck sequencer, which in this case is called the QA. I'm not exactly sure why, but yeah, atom deck sequencer. If you can see that, it communicates with the plate operator by telling it what the desired size is. And at the moment, this thing is not big enough. It might be big enough. Let's just let it run a little bit. All right, there we go. All right, so there it is. And now we've got a single quote atom here. It's got a bunch of random bits in there. It's got some more random bits over here and so forth. So this is a single quote atom that's one step away from, it's at the head of the right end of the queue. And if we let it run a little further, maybe it'll get pulled out. Maybe it'll get, more will get, oh, see, well, right. So I was going to say maybe more will get put in there, but there's only room for one more thing at the moment because our atom deck is not very big. We'd like to grow it more off in this direction, but that hasn't happened yet. So there, now it's actually packed. We've got the one here and one here. There's no room for anything. And if an insert comes in from the outside world, now in this case, the atom deck sequencer is just making up requests all by itself at random because it's a demo. See, this is the other point that, when I give a talk, I don't consider it a satisfying talk unless there's a demo. And, why do I like demos so much? It's because demos are the way you show how much progress you've made with your bottom-up engineering, how many levels you've gotten. With top-down engineering, you have a problem, and then you show a performance. Learning rate 97.2%, world record by 0.2%, or whatever it is. Whereas in bottom-up, you say, look, here's a thing, it's doing a stupid task, random insertions and deletions, but look how robustly it's doing it. Look how it's making room and getting around and so forth. It all hangs together. Okay. So in fact, that's what was going on, and I suppose we could go quick, maybe just take a little bit of a look again. Maybe I'll jump in. Right. So there you can see it now. There is the white thing is the atom deck sequencer. Those lighter blue things are single quote atoms that are in there doing it. They're moving back and forth and wrapping around. This one looks pretty full. This one's got some extra room, and so on. So that's it. Everything is alive. Everything works together to bring the data where it needs to be. It's all betting. Put it one square away. By putting it one square away, there's room to do one more insert while it's still close enough to be removed immediately. And then once you haven't got once an extra one gets in there, everybody social distances down the line and wraps around. And then when somebody gets pulled out, everybody creeps forward and so on. It's nice. It's good. Okay. That's the development story. On the research side, I finally managed to get going on the guts of the Linux kernel module for the new clean screen event engine redo. In particular, there had been two separate Linux kernel modules, one for dealing with these special pins that were for locking, the other one dealing for sending and receiving packets. But we really need to get them together so that as a result of these special pins saying, in the ring oscillator says it's your turn to do an event, they need to be able to send packets and communicate back and forth. We have gotten to that. This is code from the packet initialization thing that goes over and calls the initialization on the generalized distributed ring oscillator side, and that is now working, as we can see, because it announces its activities. I'm going to take March off. There's not going to be any T2sday updates. This is the only T2sday update in March. To focus on really cranking on this stuff. I also have some scientific writing I need to do and a bunch of other stuff. So I'm hoping to push this a lot farther. But that's the research story for now. On the outreach side, We have this short story, Search Quiet Wake, that got rejected by Asimov Science Fiction Magazine. Last time I was asking folks what they thought, whether I should try to send it to other magazines or whatever. Among the folks who did get in touch, they were saying, yeah, submit it someplace else. Try again. Maybe shoot a little lower. And it was great. And there were some suggestions in the Discord of science fiction magazines that I'd never heard of, including one called Clark's World that seems kind of interesting. It was also, a little bit, humbling to read about, because the guy Clark, who's the editor of the thing, founder, publisher, whatever it is, goes on in his blog postings about people that submit to the slush pile, just sending in stuff unsolicited. Typically they send in 7.5 stories before they get one accepted, and so on. So here I am, wrote this thing, sent it off to one place, and I'm all ooh because it got rejected. It's all right. A bigger problem from my point of view is I got some more reader feedback from a friend, and it was kind of brutal. And accessibility is the problem. That this story makes a ton of sense to me, but otherwise you have to be really kind of willing to go along with stuff that doesn't make any sense for fair chunk of time reading through the story before supposedly it pays off and it makes sense. And I'm gonna work on in March. I'm also gonna work on making it more accessible. It's a little bit challenging because the whole thing is written as if it's in the future, so it's a little extra work to figure out a reason to say stuff that would make sense to us losers way back in the past. But we'll see. And who knows? Maybe I'll even send it off to Clark's World. They have a bunch of slush pile readers, and they talk about turnaround times, typical turnaround times in days, and that's because, of course, they're saying no to 90% of everything. So we'll see how it goes. So that's the story on the story. And that is it. Oh, and I finally sent out our emails to our two latest Living Computation Foundation nerds. Once again, thank you. No T2sday updates in March. That's 2 of them off. The next one is going to be April 12th. It's like 6 weeks away. Yeah, I'm stoked. And the goals are, it would be good to build a third Lotus to get us, really get a little more sizable. Right? Get the story more accessible. Get this new clean screen stuff up to the point where it's actually interacting between user space and the Linux kernel module. And let's have a bunch of fun. And hopefully, let's not all get reduced to a nuclear cinder between now and then. I hope you guys are all right. I will put some links down below on things that I've found for helping out Ukraine. Liberty sounds like a good thing. Liberty and justice for all. I think Ukraine is going to be in the shorter end of that, given this current confrontation. So let's root for them. Thanks for coming by, folks. I hope to see you next time. Alrighty.
Thank you.